go through again the email that I sent shortly or a moment ago this morning, which was asking for you guys to go on GitHub, download all the GitHub repository again, which is what I have right here on this page in this folder. And then on the 03 data folder of the GitHub page, you would have a kb2 elevation.csv file. That is a brand new file. You need to copy this into your data folder of your project. So this elevation one, and if you were not able to complete the homework, you also need to copy the clean interpolated .geojson files. So the 2017 we produced in class, but the 2019 and the 2020 you produced during the homework. So if you were not able to do that, please copy the elevation, clean IP 2019 and 2020 from the 3 data folder of the GitHub folder into your, so now I'm going to go into my project, so LMB, into the data folder of your project. So this is what you have to have for you to be able to follow successfully today. Has everybody been able to do this? Okay. So I don't hear anything. I'm going to take that as a yes. Please let me know if you have issues so we can troubleshoot. All right, so I'm back to my personal project main folder. You can go ahead and double click that icon there to launch our studio with your project focused on it. So I'm doing that here. You know, again, that you're in a project, in your project specifically, if you see that name up there, if it's saying project none, it means something went wrong, you're not in your project. By this point, I am assuming that we all figured this mechanics out, but if you have issues, please let me know. Assuming that you are in your project, you'll come on the Files tab, and you can click on that R blue button. If you're not seeing it, you can just slide this to the right and it will pop up. But you want to click on that to go to the main folder of your project. And then you want to go under code. And I may have some more things that you don't here, but you're really looking for that 0316 yield stability partial. So once you click on that, it will pop up here on the left. You can just minimize the console if it is appearing for you like it is for me by clicking on this button here, because we know that with our markdown files, we really don't look at the console that much. And I'm just gonna resize this for better understanding. Okay, so, well, just give me a moment. Let me turn off the lights here. Okay, so today, the first part of today's class is going to be to talk about yield stability. And so the overall learning objectives here are going to be to import all the interpolated clean yield data that we have for the 3 different years for the same field. And then we're using those 3 years of cotton yield. We're going to then create year-specific spatial yield stability areas, and it's going to make more sense once we start doing it. And once we create the year-specific stability areas, we can merge all that information and derive a temporal stability area for that field. So the spatial temporal stability is going to be just one map that's going to be derived from all the 3 individual maps together. And then at the end, we're going to export this layer of yield stability so we can use in the future when it comes to management zone creation. Okay, so you can just come here on the first chunk. As you know, you can just hit the play button. So I have here a package called Tibble. I don't remember if I asked you guys to install it already. If you do not have it, you can just uncomment that install the package as Tibble and run that line by itself. And once you install it, it should be quick. You just uncomment it because we only install once. And then it should run nicely. If anyone has any issues, this is the moment to speak up. So if you were able, again, if you play that first chunk, you should run through without any errors or anything, and that's what we want to have. Okay, so now the first thing we're going to do is import each one of the clean interpolated EO data layers that you produced during the homework. So let's do that one by one, and the first one's going to be the one for 2017. So we can come here to this first chunk. We're going to use that get assignment sign again, and to import. And remember, this is a GeoJSON file, meaning that we're going to use read_sf. So SF handles all the spatial, or all the vector spatial files. So that's why we're not using a read CSV, for example, because this is not a CSV file. It's a vector file that is handled by SF. So we use read_sf. Open and close quotation marks, have a cursor blinking in between them, and hit tab. So this should show whatever you're seeing in your code folder. So to get outside of that, we do .. We come to the main directory of the project. We go inside data, hit tab again, and then we want to import the KB. At least this is how I have it named, and this should be the same for you at this point, because this was the one we did in class together. So the KB2EO 2017 clean IP, that's a long name, .geojson. So this is the file that you want to import. So if you read it, it should pop up on your environment. If we just print by just running that its own name, we're going to see here that, so, you know, I'll always check for this. So we just imported it, right? Just imported GeoJSON, have not done any wrangling on it. We want to check that it has the correct CRS for this. So it does have an NAD UTM zone 16 north, which is what we want it to be. So we don't even have to change that at this point. And I'm just going to get a summary here of this file. And what I really want to call your attention to is that you kind of did in your homework, but I didn't ask you to really look at all three together. We're just going to compare here. So on 2017, so again, same field, right? Just different years. 2017, the interpolated clean EO data vary from about 800 pounds per acre to about 5,000 pounds per acre, right? Okay, so that was just what I wanted to note here. And now we can just move to doing the same thing basically, but for the 2019 data. So we do you come to the next chunk, do that assignment. Again, we're going to use read_sf, open and close quotation marks, have your cursor blinking in between. We're just going to do .. already, because we know we have to get out of the code folder, get into the data folder, and now we want to select the proper file, right? So if you copied from GitHub, it's going to be named KB2EO 2019 clean IP. If you produce this through your homework, you may have named this differently. So you can just go ahead and import whatever it is that you named it. Just going to run that again. Again, just printing it so we can see here on the first pane, it is NAD 83, ETM zone 16 north, perfect. And then getting a summary again. So again, same field, right? Just a different year. We had yield varying from 116 to about 3,000 pounds of lint per acre, right? So we can see that this field is already, or this year is already lower yielding for this field here. And now lastly, let's just do the same for the 2020 data. So assign read_sf, open and close quotation marks, .. /tab, data, tab. And again, the way that I named it was just changing the year of the file. So for me, and if you got it from GitHub, it's going to be the KB2EO 2020 clean IP.geojson. So we run that, appears in our environment. We just run it again. We check again that NAD ETM zone 16 north, and we get a summary of it. So for this third year, we see that yield vary from about 400 to about 1,800 pounds of lint per acre. So really interesting, right? Because it is the same field, it is the same crop. just in 3 different years, we're getting, you know, kind of very different years or yields, right? If you look here, so this one is probably the lowest yielding, where we got the maximum was 1,800. We got a maximum of 2,700 for 2019. And really the highest yielding year was 2017, where we got almost 1,500 pounds of land per acre. So, you know, this is something very, very interesting to think about, because I have a note here for myself that I'll get back to that later. But it's very interesting because imagine that you're working with a farmer, or maybe in your own, you know, farms, if you have a farm, a family farm, you know, and you're trying to come up with some prescription of something. That prescription will always be targeted at improving yields, right? That's the main goal normally. So how do we use, like, if you're in a situation where you do have multi-year yield monitor data like we have here, how do we incorporate all that? I mean, do you just choose 1 year, the maximum yielding one, or the lowest yielding, or maybe the average? How do we combine all that? This is kind of what we're going to talk about today. And I hope that you're going to see how important it is to be thoughtful about this, because you may be creating different, I mean, you will for sure be creating different prescriptions, whatever that is, depending how you decide to handle different yield data. Let me see here. Yeah, I guess that's what I had there. Okay, so here's just a little bit of text that I added there for the spatial variability thought as well. So in this case, we're kind of, I mean, we're fortunate that is not the most complex case, because we're talking about the same field, three different years, but with the same crop still, right? So the range of yield values is still like within a certain limit that you would expect for that crop. What if this farmer is doing a rotation and they actually have even different crops? So let's say 1 year you have, I don't know, cotton, the other one you may have corn, which yields a lot more than cotton if you think about in pounds per acre. You know, perhaps like very, very distinct values there. How can we even combine all this data from this field? So some of the solutions that people do in scientific research, and if you're doing that commercially applied as well, is to standardize this data by some way. So one of the ways would be to use like the mean. Let's say this year, let's say it was cotton. I take the mean of that field, and then I divide all the other observations by the mean of that field. So it's going to range around 1 pretty much, or yeah, around 1. It's going to go above and below 1, or maybe the median, or maybe the max. If you're using the max to be your denominator of that standardization, then the maximum value is going to be 1, and everything is going to be 1 or less than that. So in that way, in the end, you don't even have pounds per acre anymore. You just have a value that's around 1 that just expresses how much yield you got from that year. And this is important because it's going to pretty much remove the effects of the crop right there, and to some extent of the year as well. And mostly, if you're talking about one field, we're talking about weather variability.
Yeah, I'd like to ask you a question about the comment you just made. When we're standardizing, for example, using the maximum yield, isn't that a little bit dangerous, because the maximum yield is artificial because we limited it based on some cutoff that is somewhat arbitrary, right? I know it still standardizes it, but doesn't it maybe skew the data a little bit?
Yeah, I mean, after all, I mean, I agree with you, and I think it's, well, I was going to say it's dangerous if you have outliers, like wrong outliers on the maximum side. But I mean, having an outlier is dangerous for any one of them, really, because the mean and the median to some extent are going to be affected by outliers if you have them in the data. And I've never seen a comparison of two different methods in the same paper, or I haven't read a paper like that. But my impression is that the variance within the data set is still going to be the same. You know, it's just the values are going to change depending on which one you're standardizing to. And so, yeah, my intuitive impression is that like the analysis itself and the results of the variability that you have in the end are not going to be that different. But I agree that like having standardizing by max is perhaps a little bit less ideal than by the mean or the median, really. I would actually prefer the median, because I don't know if you guys ran into this conversation, but the mean is going to be affected by outliers and the median is not as affected by outliers. And so the median is going to be a better central tendency statistics of the data in that sense. What do you think, George?
Yeah, right. I agree with you. I just get a little bit uneasy about, you know, artificial edges that we've created. So I agree. I prefer to use the median always.
Yeah, awesome. And something that, if you think about it, if you do use mean, median, or max to standardize, the output of that is going to be numerical, right? It's going to be a ratio. So let's say we have an example here. So let's say that the mean of a field was 1,500 pounds per acre. So we're going to divide all observations by that number. So let's say if you have, if you're looking at an observation that was exactly as the mean, so divide the same number by the same number, you get number 1, right? So everything is going to be still a number and continuous around 1 if you're doing by the mean or the median. And another way of standardizing is to use quantiles. And this is a different case, and this is kind of similar to what we're going to be using today. It kind of involves some of that, where we define the quantiles of that yield distribution, and we say let's say all points between the 0 and the median, so the 50th quantile, are categorized as low yielding, and everything from the median above is high yielding. Or you can even break that into 3 categories. So the 0 to 33rd quintile, 33rd to 66, and 66 to 100th quintile. So there are different ways of breaking that by quantile, but the main difference is that your outcome is categorical. It's going to be low, high, or low, medium, high. It's not going to be a ratio anymore. And that has implications on how we can use it. And we're actually going to be using the second approach here, just so you guys know a little bit. So using this, the quantile, and why are we using the quantile approach is basically because the paper that I followed, that has a similar structure to what I'm doing here, use the quantile, and I thought that was a very clever way of combining spatial, so within a field, and also temporal, so the same field across different years, into one index number. Okay, so to use the quantile approach, we have to first, in our case, we're going to calculate the median. So that's the 50th quantile of the distribution of the yield for each year. And then say whatever is below the median is low, whatever is above the median is high yielding. So let's first do that for the S17, so the 2017 data set. Let me check my cheat sheet here. Okay, so we're going to use that assign symbol, and then the first thing we're going to do is call this yield IC17 object, which is the one that we're using here. And then we're going to use a pipe. And so one thing that may, perhaps right now it's not going to make too much sense, but it is that we're going to use a function called, so if you hit tab and go to the next line, it's called row names column. And we're going to say var equals ID. Let me check and make sure that this works all right. Okay, so if you do that, I just want to tell you why we're doing this quickly. So in the end, I want to merge all of the 3 years into one data set. And to do that, we have to have a common shared column that at this point right now we don't have. So if you just look at yield, we have yield values which change, of course, this var1 var is NA all across, and then we have the geometry, the polygons of the grid. So we do not have a common variable to merge the three data sets through. So that's what row names to column is doing, is basically, even though we're not seeing row names right here, but imagine that it would just be numbered 1 through the total number of rows on the side. The row names to column is just extracting that and creating an actual column with that ID. And we're going to do this for all of the three data sets. And now, so I just ran that and I printed the result. You can see now we have this column ID, and it's called ID because we said right there, and it just has this running number 1 through the total number of rows. Okay, so the next step here is going to be, we can use a pipe, and I want to extract the median. So I want to calculate the median and create a new column here that's going to have that value all the way down. And it's going to be just one value all the way down this column because it is the median of this field in this year. So to do that, we're going to use the mutate function.
Dr. Mathis, I have a quick question. I don't
Yes.
mean to interrupt your progress, but so the row names to column, how I assigned the numbers starting at 1, then down to 10, was that something that we coded, or did it just automatically populate? Did it just automatically know to populate it with numbers? Like,
It pretty much just automatically did it. Yeah.
okay.
Because it kind of has that index behind the scenes, but we don't normally use it. So this is just explicitly bringing that index into the data frame, but it's the structure of it is already there.
Okay, thank you.
Yeah, absolutely. So, so the next thing here, we're going to create the median. I want to call that this column, I want to call median yield underscore pound per acre. So it looks a little bit weird to see, but that's what we want to do it. And the way that we do that is you say an equal sign, and then there's a function called median. So we say median, and then we have to see the name of the column that we want to compute the median for, which is this one here, the IP yield underscore pound per acre. So it's basically going to take all those data points and extract the median of that column, create a new column, and just populate that single value for all the way down the table. So if you run it and we print it, and it's going to be on the side here. So if you're not seeing, you can just use the arrow, and you're going to see now that the median was about 3,000 pounds per acre, and is the same value all across. So it's not changing as it is our yield. So our yield value is changing. The median is the same for the entire field. Okay, so you can add a pipe to the end of it, hit tab, and here's what we're going to do. We're going to use a mutate, and I want to create a column now that's going to do the following. It's going to look at yield, the actual yield value, and is going to compare it with the median. And if the value is below the median, then this new column that we're creating is going to have the value saying low, meaning low yield. If the actual yield is greater than the median, then this column is going to have a value saying high, meaning high yield. So it's going to be another column that's going to have two values, low and high, and that the assignment of the value will depend on whether or not actual yield is lower or greater than the median of the data set. So to do that, I want to call this SN yield, and the SN is for spatially normalized yield. Is kind of the way that the paper that I based this off uses. So so here this column is basically, as I was telling you, we have two conditions, right? If it's lower than median or greater than median. How do we incorporate conditional or conditions like that in programming, generally speaking? Like if you're doing in Excel, for example, how would you include a condition? Any guesses?
Using if.
Yes, Janice, thanks. Using if. So in programming, we would use something like if this is true, then that happens. If this is false, then this other thing happens. Here in our case, we could use a function called if else, which does exactly that. I'm not going to use the function if else, because the function if else, if you have more than, so we only have 2 conditions, but sometimes you have like 10 conditions or more. If you use if else, you start nesting if else inside if else's, and gets very complicated very fast. So I really want to show you something here that is more intuitive than if else, and it's going to scale when you have more than 2 conditions. So to do that, we use the function case underscore when. So case when is the name of the function. You can just open and close parentheses if it hasn't happened. Make sure that you have your cursor in between the open and closing parentheses of this function, and hit enter just to give some space, because it's going to be easier to see what's going on. So it's going to be SN yield equals case when open parentheses, some spaces in between, and then that all ends up, you finish that with 2 parentheses again. Okay, so well, the condition that I want to, so we're going to use variable names to set the conditions that I just told you. So we're going to compare our actual yield, which is that IP yield underscore pounds per acre. If this value is greater than or equal, so this is how you would specify. If you do the like the opposite, if you do equal greater than, it's not going to work. It has to be in that the equal has to come afterwards. So if yield is greater than or equal than the median yield pound per acre, which is also a column in our data frame, then, and the way that we tell then is using tilde, then we want to give this column as an yield the value high. Okay, so just walking through that again. If our observed yield is greater than or equal to our median value, then the spatial normalized yield is going to have a value of high. Okay, so we did tell it what happens when it's greater than, but what about when it's lower than? We add a comma here, hit return just for easy to see this code easier. And we're basically going to do the opposite. So if yield is less than the median, then that column is going to be called low. Okay, now I'm just going to remove the extra spaces just to make it easier to see. You should be seeing this. I just want to run this and print. I want to leave the code up there in case you're still catching up. But just let's see here. So the first observation is like 2,700 pounds per acre. We know the median is 3,000 something. So this value here was classified as low, right? As you would expect based on what we coded. So now we have this column here that we created as an yield, which is right there. That's going to have values of high or low, depending on the actual yield compared to the median, right? So I'm just going to come lower here just to browse a few more pages to see if we find a high. Yeah, so I saw a few going by. So there's a high there, there's a high there, right? So it just applied this condition to all of the observations in this data set and doing the comparison, assigning low or high. If you had more, let's say if you had more conditions, which I'm not going to show here to not make things complicated, you would simply just add a comma and keep adding conditions all the way until you're done with them. So case when is very useful for this. Instead of using nested if else's, which are crazy and very complicated to read, case when saves the day. Any questions?
Mine is giving me an error saying it's not finding IP yield underscore LBAC, but it ran the first, like mutates, it was fine, the first mutate that we used it in, but then when I got down to the high and low lines, it didn't find it for some reason.
Okay, so what I would do is starting, so the data set that we're starting all this is the yield IC17. If you just highlight it like I have now, and do run. So on a Mac would be command return, on a PC would be control return. it's going to print that data set lower here. So this here should be, so this is where I got the name from. Perhaps when you were coding on your side, maybe you name it a little bit differently. And it really doesn't matter if you did, it's just that you would like, so that name there is matching this name here.
Yeah, they're all matching.
Huh.
Still
And
not
still,
finding it.
and it's still not working.
Yeah,
Would you like to share your screen?
sure. It says I cannot, let's see. Can you see it?
Yes. Mhm.
There you go.
Oh, I guess I know what's going on. So I think you're missing a pipe on row 79.
Here,
Like, yeah, at the end. Yep. So right there, you should have a pipe to connect that with with what comes after.
yep,
There we go. Yep, that was it.
easy,
Awesome.
thank you.
Yeah, no worries. All right. Let me share again. Okay, so now that, so this column here that we just created, let me just print this again so you see the S and yield is really the key column here that we're going to use moving forward. Because this is what we're going to use then to create a temporal stability when we compare the spatial stability with all three fields. So with that, I just want to, so we don't need to know the median anymore. We don't need this var1 var, which was a result of the interpolation function, which is really NA all the way down. So it makes really not much sense. I just need some of the variables. And just to keep things clean, I want to select only the variables that we're going to use further. So to do that, you can do a pipe here, hit return, and we're going to use the function select. Now, here's a trick that you will run into if you're doing spatial analysis in R. There are a few different packages besides, so the function select that we want to use is from dplyr package. There are at least a couple other packages that have that are for geospatial data analysis in R that also have a function called select. So how do we make sure that we're using the proper select function? To do that, we call the package name, which is dplyr, use the colon symbol, and then we say select. So this is making sure that we're using select from dplyr package. And I kid you not, I spent perhaps hours one day trying to figure out why my select function was not doing what I wanted until I realized that it was using select from another package called raster, which does nothing what select from dplyr does. So this is just a quick tip for you there. So
can I add something?
yeah. Mm-hmm.
Yeah, so when we are writing the function select and we press tab, it shows the package it actually is from, right?
Yeah, you mean like one? Yeah. Mm-hmm. Shows right there. Yes.
So we can just select this one and it's going to specifically be from DPLY.
Yeah, in our case here, I don't think we're using I don't think we loaded the package that has the conflict, which is I know package raster has a conflict with the select. So in that case, it's not loaded. So maybe we wouldn't have this issue here. But still, I think it's better to explicitly say where you want it to come from, because I assure you select is a very popular name among package developers.
Yeah. Okay.
So it's better to be, to be certain of where that's coming from. Yeah. And this is very interesting because it doesn't happen as often for other functions. You don't see us using this syntax for all the functions. It's just that select is in fact a very popular name for different developers in different packages that do different things, right? So just to make that clear. Yeah, is that okay? So I want to select the ID column. As I mentioned, we're going to use this ID column to merge the data sets later. And then also I want the true yield, so the IP yield pound per acre. And I also want the SN yield. And here's a quick trick about the select function as well. We can specify the columns that we want, but you can also rename them right here in select. And to do that, I just want to add, so here I want to call this SN yield underscore 17, just so we know that this is the spatial normalized yield values for the 2017 data set. So I just have to say the new name, which is what I just wrote there, equals the current name of that column in this data set, which is SN yield. So that's what you want to have in your code. And then finally, we are keeping the geometry as well because it is a geospatial data. We want to keep that part of it. So if you run it, you should see your ID column, your actual yield, the SN yield values lower high, and the geometry at the end. So this is basically us finishing to process the 2017 data set. Okay, everybody, if anyone has any issues, please speak up. I don't hear anything, so I'm gonna keep going. Okay, so I am a huge fan of maps. I like to visualize my data. And so that's what we're gonna do next here. So what I wanna do is plot the value low, so the variable SN yield, which has values lower high. So we see in that field where lows and where highs were located. And I also want to save this plot to an object that I'm calling S17 map. So you can just use the assign symbol. We're going to start our plot as always using ggplot. And right now we are not going to say anything at the level of the ggplot, just going to add a plus and hit tab or return. Oh, something great to remind you guys too. So when we're doing data wrangling, notice how we use the pipe, right? We've been using the pipe for some classes now. However, when we are inside ggplot, we use plus. It's just a different notation that the developers chose, but I just wanted to make you aware of that. If you try to use a plus here, it would not work. If you try to use a pipe inside ggplot, it would not work. Just so you're aware of that. Okay, so because I want to plot this layer, this object here, which is it is a spatial object, a vector spatial object, we're going to use geom underscore sf. And then we have to say data. So data equals s underscore 17, which is what we just produced above here, s7 underscore 17. Add a comma. I want to hit return, and then we specify the aesthetic. So we do that by using the function AES. And I want to say that fill, so the fill of the cells of the grid, I want them to be colored according to, let me just print here so we can see, according to SN yield underscore 17. So that's how I want them to be colored. And then you come outside of the AES function, add a comma, and you can say color equals NA. And again, when you have like a shape like a polygon in this case, fill is whatever is inside of it, and color is whatever the color is on the outline of that shape. So this is why color is NA. I don't want any outline color, but I want the inside of it, the fill, to be colored according to this variable. Okay, so I mean, we can just run this at this point and show in the map so we can see. So this is pretty much what we can see there. So for this field in 2017, the high yielding points kind of concentrate towards here, the southwest part of the field, and the low ones, and also a little bit here in the north, but then everything else is the low yielding areas. And I want to spend a little bit more time on this plot specifically, because then we're going to just copy and paste for the other fields. But I want this to look nicer. So I want to add a plus there, and we're going to use scale underscore fill underscore viridities as we've been using. And I just wanted to show you here, is really, at this point, is really just for you to see how it works. But it has an option argument that it takes values, I think, A through age. And so we can just specify here, you open and close quotation marks. Let's just use the option E. And you can just print that. Oops, that didn't work. Maybe because we need varieties _D for discrete. Yeah, so sorry, it's a scale, fill varieties D, and this D here stands for discrete because our variable is low or high, it's not a number anymore. So if you run that, this is what you should see now. A couple more things I want to do here. I just want to add a plus, hit enter. And then we're going to use a function called labs, which stands for labels. So inside this function here, we can change title, subtitle, how this S in yield appears here. But right now, what I really want to show you is just to change the title or to add a title because it doesn't have a title yet. So let's just say title equals open and close quotation marks 2017. So if we run this, let me go back to my code so you can see it. Now it says 2017 on top. This is going to be helpful when we combine different maps into one map to show. I also want to use a theme called, so if you add a plus, hit return, I want to change the theme of this plot to theme map. And let me just see, oops. So theme map is coming from package DG themes. So it's not native to ggplot, but if we just run that and print the plot, you see how now things became a lot more clear, right? So we don't have anymore the axis information. We don't have anymore the background with the different ticks going up and down and left and right. So it's a lot simpler here. I prefer that and I wanted to show you that, but it's again, if you in your plot, you do want to show the coordinates, west and north, you can always use a different thing. And then lastly, I want to just change where this legend is. I want to make it move to the right. So to do that, we would add a plus, hit return. There's a function called theme. So here's a quick difference. Theme _ something changes a whole bunch of defaults of the plots. And you don't really have too much control over whatever this function here is doing because it's all predefined. If you want to then go further and change something specifically yourself, you have to do that through the theme function after you call the theme _ something. So in this case here, the theme function has an argument called legend _ position. And I just want to say right. So open and close quotation marks and say right. So it basically just changed the location of the legend to the right side of the plot. Okay, I'm just going to leave the code here for a brief moment. And move on. All right, so we're pretty much done with 2017 for the spatial data. What I did then is I left all the code for you for the 2019 one because it's basically just repeating what we just did above. The only difference is that now we're changing the incoming or the starting data set, right? We're using the 2019 one instead of the 2017. So you can just go ahead and run it. And you can see again that we have the columns that we wanted. So ID, S, and yield. Oh, and also notice here on the select here, I rename S and yield to S and yield _19, just so whenever we merge all these three data sets, we know what year that's coming from. So this is what we have. And then you can just go ahead and run this for 2019. And okay, I want you, so stay here, stay looking at the 2019 one. I want to scroll up on my end to 2017 one. Well, you know what? Let me actually just pop up that output of 2017 and I will scroll down so I can also see them together. So we do see like overall a similar areas that were high or and low in one year also were in the other year, but not all of them, right? So what, like on this side here on 2017, we had some more high yield points than we did in 2017. Sorry, on 2019, we had some more here than we did in 2017. It changed a little bit here as well on this side around here. On 2017, we had more high yielding on the bottom here than we did in 2019. So we do see that things changed, and this is just 2 years, right? And this is not even including the year that was the lowest yielding, which was 2020. So this is just, you know, to make again the point of why do we have to think about these things and take into account. So again, I left for you the code so you don't have to just repeat for the 2020. Again, the only difference is that the incoming data set is different. We're saving to an object called S20. And in the end here, we're renaming that variable to SN yield 20, just so we know what is that it belongs to this year. So please go ahead and run that chunk and also run the map. Ooh, this one looks a little bit more different, I guess, because so something that happened in 2020 that we had not seen previously is this like this mix, I guess, of low and high within the same area. It was more consistent, I feel like, if we just come up here, like we had fewer intruders inside each other, whereas here we see a little bit more of a mix in 2020. All right. So everybody should have been able to get to this point successfully since you have the code there. And now what I want to do is just, so we have these 3 maps, you know, and again, it's important, I think, to see them together side by side. To do that, to combine these 3 different objects, I will use a package called patchwork. Now you may, if you just run that library patchwork, and if it gives you an error saying you don't have it, then you will have to install it. I don't remember again if I asked you to install this previously. So if you have to install it, you know the drill. You basically just do an install packages, open and close quotation marks, and paste the name of the package there and run it once. Once you install it, you can just delete that and just keep it like this. Okay. Yeah, I guess that was probably enough time if you needed to catch up on installing that. So assuming that you have that, patchwork is really, really easy to just combine maps in a very, very convenient way. So what we're going to do basically is just, let me come here. So I'm looking at my table of contents on the right. I'm going to go to the chunk named S17 map. And I'm just going to copy this name here, S_17_ map. You didn't have to do this, but I just wanted to show you how that would work if you needed to go back to a previous chunk. I come back to the chunk named all maps, which is where we were, and you just basically paste the name. So S17 map, and then you add a plus. I just pasted S17 again, and you're going to change to 19 because that's the other object. And I add a plus again, and I add S20 map. So this plus here it can be a little bit confusing because it's not ggplot at work. It is actually patchwork package at work because it knows that you're combining different ggplot objects. So remember that these objects here were where we saved each one of the plots. So it knows that we're talking about ggplot objects, and if you're using a plus, patchwork sees that and just combines them. So if you run them, this is what we're going to see. I actually wanted to have this legend on a different place of this plot. So to change that, we can just add a plus to the end here, hit return just to make it easier to see. And then the patchwork package has a function called plot_layout that really lets you change a whole bunch of features of the layout of these combined plots. The one that I want to change is called guides. So guides is a synonym to legends, and it has a value called collect. So if you just run that, It should, what it did, it basically, if all plots had a legend, you would have collected a legend, individual legends of all plots and show them on the right. However, only 2017 had a legend. For 2019 and 2020, I removed the legend altogether. So if we just, you can stay where you are, just want to show you. So the 2020 plot does not have a legend. 2019 also does not have a legend. The way that I removed the legend from those two plots, and it was by design, is just inside that theme function, the legend position, instead of saying right or left, I just said none. So it basically removes the legend. And I just did that to make it nicer to visualize when we combine all them. Okay. So now looking at them together, like side by side, I think it's even easier to really see how like some areas are probably always high, some areas are probably always low, and some areas are changing depending on the year. And because this is the same crop, it is the same field, this is probably being mostly driven by weather and potentially by management, because we really don't know how the farmer was managing the field differently from year to year. But I would say weather is probably the main driver. That would be my guess. All right, so just recapping now, we did the spatial normalization to high and low for each one of the three fields individually. Now the goal is to combine this information from 3 different years into one map that we're going to classify, incorporating the temporal aspect of being different years.
Neil, before we do that, let me make a couple of comments about these really nice maps that you've created here, since I do have experience with this field. So the map from 2020 that shows, these little patches of lower yield in the middle of high yield and little streaks are really an artifact of the weather. What happened was we had a number of tropical storms that came by. And because the cotton was taller in parts of the field that generally have higher yields, it got knocked down by the winds. And so when the machine was coming through to harvest, the cotton was lodged. In other words, the stalks had fallen and the machine was not able to make good progress. So I think particularly if you look at that streak, it's at the very southern end, you have a streak of low yield in the middle of that high yielding area. That's, yeah, exactly where you're pointing. That's what happened there. The machine was just not able to harvest effectively because of the lodging in that particular pass. So they were going extra slow. We may have clipped some of those data because of slow speeds. I don't know exactly, but that's more or less what happened there.
That's awesome. It's really interesting because I didn't know that information, and just by looking at it, we can tell that speckled effect, but it's really, really great that we can now connect that to what actually happened and understand better. Yeah, thanks, George.
Dr. Velides, can I ask something?
Sure. Mm-hmm.
How a comparison with different thresholds help us evaluate the yield in different temporal series? Because every map has a different threshold.
That's
so
right.
maybe in 17, a pixel that has a high value in 2020, in 2020 it's going to be low.
That's a great point, and
it might be exactly the same pounds per acre.
Right, and in fact, that there are 2 sides of that coin, and it really depends on the objective that you're trying to do. My objective showing you guys this was first to show that certain areas of the field can be consistently high or consistently low, or inconsistent, like high in one year, low in another year, depending on the weather. To do that, you really have to normalize that yield value to whatever happened with that field on average, in our case, using the median, right? Because if you don't, then exactly happens what you said. Like, let's say if instead of having high and low, we actually have the yield values, then we're confounding information in that. And it's difficult for you to really say that something was high or low, because how do you judge high or low, right? So if you, let's say our goal here is to identify areas that are stable high, stable low, or unstable. So this would be the way to go. If your goal is to actually, let's say, predict actual yield, like a value of yield, then you would not normalize like we did. You would still keep that actual observed yield value, because that's what's going to give you that information that is probably mostly in this case affected by yearly weather differences, which is very important, right? We know the weather plays a key role in yield formation. And so if your goal is to predict yield, then I would not normalize. Our goal here is not to do that. Our goal is just to understand what areas are consistently high, low, or unstable compared to the median of the field, like to normalize it that to that specific field and year and crop, so we can compare different years altogether.
Well, what about using one threshold for the whole, for throughout the years? That wouldn't help. So we would have an average threshold, let's say. I don't know exactly how, but I'm just thinking.
Yeah, that is also a great point. Is like, let's say one thing that we could have done that we did not do here is to perhaps take the median of all 3 years combined, right? Which is, I guess, is kind of what you're saying there, right? We could have done that too. Yeah, I mean, the specific reason why I use this approach is because I agree with the theoretical background of it, and also because there's a really nice paper in Nature that defines a very similar protocol. So it is something that people, this is not something that I sat at my desk and decided to do, right? It's something that other people are also using and validating. So I wanted to show you guys something that was produced by, that's already published, not just something that I'm coming up with, but it also leaves room for exploration, right? So you guys have the code, and I think it would not be too complex if you just wanted to combine all 3 data sets, get the median for the entire data set, and try out. Because my guess is that it would have different aspects. And also, I guess, always coming back to the main goal of this analysis. If we do that, let's just think through it. If we do combine all data sets, get the median of all 3 years, and use that to define high and low, it has its pros, but also has its cons. What would happen then is that median is being affected by different years, which are mostly affected by weather. So that median is affected by yearly differences in weather, right? And so it makes it a little bit more difficult to understand the conditions that made an area being high or low, because now we're mixing everything. The way that we're doing here, we're pretty much saying, regardless of the weather, or not regardless, but accounting for the weather and the effect that weather had on yield potential on a given year, I want to understand if an area is high or low, right? Because let's say in poor weather, maybe some areas will produce more than others, and on good weather conditions, maybe that will shift, or maybe it will not shift. Right? We know that, for example, if you think about it, something that we're going to be seeing a little bit more in the next exercise with the terrain aspects. Why is terrain so important, and why does it have a direct connection with yield? And how that can change from year to year is. I just want to give you one example of that. So let's say you have a sloped area of the field where on wet years it accumulates water. So on wet years, that lower part of the field yields less. However, on dry years, that low part of the field also accumulates water. And now you have more water for a crop that is needing that water because it is a dry year. So one year to the next, a wet and a dry year, you can have a high or a low yield because of that weather interacting with terrain, right? And this is something that we would be able to assess using the year-based median like we're doing here. And if you take one overall median, maybe that's not going to be as clear. Does that make sense?
Yeah.
Sorry, I know I gave you a very long explanation. Just my brain.
No, I was just thinking, so pretty much we're just taking the weather out of the equation and just look at the soil variability and I guess nutrition or whatever affects them.
Yeah, I mean, yes, and assuming that management was very similar, right? We don't know. I mean, I don't know that. Maybe George
Yeah.
wouldn't, but I guess that's not the point. It's just that whatever was changing from year to year, we're accounting for when we do the year-based median. Any other comments or questions? That was great. Great discussion. Thanks, Janice. Okay, so we are at 10:13. I want to give you guys a little bit of time to walk and, if you need a restroom break or whatever. So maybe let's reconvene in 5 minutes, like 10:20 to keep going. Combine all these three maps into one spatial temporal map. And we're going to do that next. So yeah, if you guys want to take a 5-minute break.